The Large Hadron Collider at CERN is insanely successful as the most powerful particle accelerator ever built. The LHC recreates conditions similar to those just moments after the Big Bang by accelerating particles to near the speed of light and smashing them together. There, it allows scientists to explore the fundamental building blocks of the universe, potentially leading to new discoveries that could transform our understanding of reality. But now, some scientists believe that beneath its scientific exterior, the colossal machine stretching over 27 kilometers might be pursuing deeper secrets involving dimensions, portals, and ancient technologies. Even Whitney Webb, a renowned researcher, is also delving into this intriguing theory, suggesting it might change everything we thought we knew about science and history. So, what hidden truths could CERN be concealing? Could it open a doorway or a tunnel to another dimension? All this and more will be discussed in today's episode. Let's start with the truth that the dimensions of the universe are a vast and complex topic, touching on both the observable and theoretical aspects of cosmology. The universe, as we experience it, has three spatial dimensions: length, width, and height. These are the dimensions in which all physical objects and phenomena exist and move. These dimensions are familiar to us in everyday life and are described by Euclidean geometry. Time is often considered the fourth dimension, a concept revolutionized by Albert Einstein's theory of relativity, which introduced the idea of space-time. In this framework, time is intertwined with the three spatial dimensions, forming a four-dimensional continuum. This means that the position of any event in the universe can be described using four coordinates, three spatial and one temporal. Time, therefore, is not an absolute measure but is relative, depending on the observer's velocity and the gravitational field they are in. In everyday experience, we perceive time as a linear progression from the past, through the present, to the future. However, in the context of relativity, time can bend, stretch, and contract depending on the relative speed of observers and the presence of massive objects. This interplay between space and time is one of the key insights of modern physics. Beyond the four dimensions, three for space and one for time, theoretical physics proposes the existence of additional dimensions that are not directly observable. These are often discussed in the context of advanced models. For instance, string theory is one of the most prominent frameworks that suggest higher dimensions. In string theory, the fundamental building blocks of the universe are not point-like particles but tiny vibrating strings. These strings can vibrate in multiple ways, and their vibrations determine the properties of particles. For string theory to be consistent, it requires the existence of additional dimensions, usually 10 or 11 in total, depending on the version of the theory. These extra dimensions are thought to be compactified, meaning they are curled up so tightly that they are imperceptible at macroscopic scales. The idea is analogous to a garden hose. From a distance, the hose looks like a one-dimensional line, but upon closer inspection, you can see its two-dimensional surface. M-theory, an extension of string theory, posits the existence of 11 dimensions. This theory unifies the various versions of string theory into a single framework and introduces the concept of membranes, or brands, which are multidimensional objects that can exist within this higher dimensional space. Our universe might be a three-dimensional brane floating within a higher dimensional bulk space. This leads to intriguing possibilities, such as the existence of parallel universes or other brands with different physical laws. But do alternate dimensions exist? Could we travel to different dimensions or parallel realities? While many people believe that this fascinating idea is just a concept in science fiction and theoretical physics, some scientists argue that CERN's LHC could make the impossible possible. For them, the colossal machine, stretching over 27 kilometers, hidden deep below the Switzerland and French border, is not just a massive tunnel, it's a portal to the secrets of the universe. At its core, the LHC is like a giant racetrack for tiny particles called protons. Picture it like this: imagine the LHC as a colossal tunnel with two lanes running in opposite directions. Inside these lanes, scientists send protons, particles smaller than atoms, whizzing around at speeds close to the blink of an eye. These protons are so small that if you could shrink yourself down to their size, you'd be smaller than a grain of sand in a vast desert. But here's where the magic truly happens: it's not just a matter of firing a few protons at each other. No, scientists at CERN unleash an astonishing 100 billion protons in each direction, creating a collision course of epic proportions. And you won't believe how many of these tiny particles actually collide. On average, out of the staggering 100 billion protons hurtling towards each other, only about 50 or 60 of them manage to collide. To put this into perspective, imagine standing in the midst of a bustling city with billions of people rushing past you. Now imagine trying to spot just 50 or 60 individuals out of that massive crowd. It's an incredibly tiny fraction, yet each collision holds the potential to unlock profound secrets about the universe. This remarkable feat is repeated over and over again, with scientists observing these collisions a mind-boggling 30 million times per second. With approximately 3,000 bunches of protons hurling through the LHC, each containing over 100 billion particles, the result is an astounding 1 billion collisions per second inside this massive machine. These collisions are sufficiently violent that they are expected to briefly create conditions similar to those obtaining countless eons ago, not long after the Big Bang, when the entire universe was still inconceivably small. It was smaller than a proton for quite some time, seemingly still, with all the matter that nowadays makes up the vastness of space and galaxies packed in somehow. Naturally, some extremely strange phenomena are to be expected when one mangles the very fabric of spacetime itself in this fashion. Various eccentric theories have claimed that this would doom humanity in one fashion or another, perhaps converting the entire Earth, everything on it, and possibly the rest of the universe into strange-let soup, or some other frightful subparticulate mixture. It has also been suggested that careless experiments at the LHC might inadvertently call into being a miniature black hole and carelessly drop this into the center of the Earth, causing the planet to implode. It's certainly hoped that the button marked "Call Black Hole into Being" on the control board has some kind of protective cover over it. Evidently, these critics were wrong. We're still here in 2024, and though it can sometimes feel like we're living in a hellscape, we are, at least for the moment, still a pre-apocalyptic society. In fact, the LHC ran successfully at the headquarters of the European Council for Nuclear Research for several years before shutting down for updates in 2018. In that time, the particle accelerator facilitated some of the biggest international science collaborations the world has ever seen, resulting in the discovery of an elementary particle named the Higgs boson, also known as the God particle. But now, doomsday fears are rising once again as the Large Hadron Collider is springing back to life to continue Run 3 operations at the energy frontier, a new period of data-taking that will see it create collisions at unprecedented energy levels. This time, it's not mere black holes that people are anticipating. Some scientists have speculated that black holes might alternatively act as spacewarp wormhole portals into alternate universes. This would seem to align with the remarks of Sergio Bellucci, Director for Research and Scientific Computing at CERN. Out of this door might come something, or we might send something through it. In fact, the possibility of creating a black hole in a lab is a goal that scientists are actively pursuing, one that could allow researchers to answer many fundamental questions about quantum mechanics and the nature of gravity. A black hole typically forms when a star, much more massive than our Sun, dies. While the outer layers of such a star explode outward in a spectacular supernova, its core crumples inward, pressing down toward its central point with so much power that no known force in the universe can stop it. This results in unimaginable mass and density, whose gravity is so strong that even something traveling at the speed of light couldn't move fast enough to escape its pull. These kinds of black holes are common throughout the universe. However, as long as something doesn't get too near a black hole, it remains safe. Only within a spherical boundary surrounding the black hole, known as the event horizon, would a person or object get pulled inexorably inward. Enormous black holes have a big event horizon with a diameter of millions of kilometers, whereas smaller ones have more minute event horizons extending just tens of kilometers across. Fears about the LHC creating a black hole originated with the fact that in Einstein's special theory of relativity, mass and energy are interchangeable, hence the famous equation E=mc², where c is the speed of light. Because a super collider slams together protons at unbelievable velocities nearing the speed of light and energies, all sorts of strange and exotic particles can pop out, potentially including a black hole. But creating a black hole with even a microscopic event horizon would require billions of times more energy than the LHC is able to produce. Even if it could produce such a black hole, that object would quickly lose energy and dissipate in the blink of an eye. However, there are a number of theories that predict the existence of extra dimensions, not merely the three spatial and one-time dimension we know to be present in our four-dimensional spacetime, but at least one additional spatial dimension that exists in our universe. While we can't quite access those dimensions at the energies we've probed, it's conceivable that at scales smaller than those we've examined, which correspond to higher energies, these extra dimensions exist. If these extra dimensions exist, one theoretical possibility is that it might be possible to create black holes. Over the years, scientists have looked into the possibility that black holes could be wormholes to other galaxies. They may even be, as some have suggested, a path to another universe. Such an idea has been floating around for some time. Albert Einstein teamed up with Nathan Rosen to theorize bridges that connect two different points in spacetime in 1935. But it gained fresh ground in the 1980s when physicist Kip Thorne, one of the world's leading experts on the astrophysical implications of Einstein's general theory of relativity, raised a discussion about whether objects could physically travel through them. Indeed, Thorne, who lent his expert advice to the production team for the Hollywood movie Interstellar, wrote that we see no objects in our universe that could become wormholes as they age in his book The Science of Interstellar Star. In the words of Thorne, journeys through these theoretical tunnels would most likely remain science fiction, and there is certainly no firm evidence that a black hole could allow for such a passage. But the problem is that we can't get up close to see for ourselves. We can't even take photographs of anything that takes place inside a black hole. If light cannot escape their immense gravity, then nothing can be snapped by a camera. As it stands, theory suggests that anything which goes beyond the event horizon is simply added to the black hole. What's more, because time distorts close to this boundary, this will appear to take place incredibly slowly, so answers won't be quickly forthcoming. As Douglas Finkbeiner, professor of astronomy and physics at Harvard University, said, "I think the standard story is that they lead to the end of time. An observer far away will not see their astronaut friend fall into the black hole, they'll just get redder and fainter as they approach the event horizon as a result of gravitational redshift. But the friend falls right into a place beyond forever, whatever that means." Put simply, while opening a portal to another dimension is still just speculation, we can't rule out this bold idea. After all, the universe is indeed mind-boggling. It's vast, mysterious, and full of wonders that challenge our understanding. When it comes to the possibilities of what could exist or happen within it, many ideas and theories are still being explored, from the nature of dark matter and dark energy to the potential for multiple dimensions or parallel universes. The possibilities seem almost limitless. In science, we strive to rule out impossibilities by testing hypotheses and gathering evidence, but some questions remain open-ended and speculative. The idea that anything is possible or that we can't rule out certain phenomena reflects the awe and curiosity that drive our exploration of the universe. In addition, although a black hole can move us to it, it also can offer an even more grim fate, the possibility of destroying the Earth itself entirely, perhaps even swallowing it whole. While life on Earth is expected to come to an end within 2 billion years as the Sun continues to swell, expand, and heat up, we expect the Earth itself to stick around for another 5 to 7 billion years until the Sun becomes a red giant, at which point it will engulf Mercury, Venus, and possibly the Earth as well. But there's always the possibility that a black hole will randomly, as the stars and stellar remnants dance throughout the Milky Way, pass into our solar system, devouring our planet in the process. But is there any way we can know when it's coming? Will there be a warning, or will we simply be swallowed up before knowing what's going on? To be honest, this is a challenging question because, while the black holes that we know of are too far away to swallow us anytime in the foreseeable future, we know that there are plenty of invisible lurkers out there, and those are perhaps the most dangerous ones of all. So far, there are only 4 main ways we know of to directly detect black holes. One is through their emissions of light, particularly X-ray light. You might immediately object and say, wait a minute, I thought the defining feature of black holes was that they are black, as in no light can escape from them. And that's true, from within their event horizons. There's an imaginary surface you can draw around any black hole, a sphere for a non-rotating black hole and a flattened oblate spheroid for a spinning black hole, that separates its outsides from its insides. If anything crosses over to the inside of the event horizon, it cannot escape, it must inevitably hit the central singularity, where it only adds to the black hole's mass and energy. but the event horizons of black holes are very small. While stars like our Sun are more than 1 million kilometers across, and giant stars like Betelgeuse can be larger than Jupiter's orbit around the Sun, over 1 billion kilometers across, black holes are the densest objects in the known universe. A black hole of the mass of the Sun would have an event horizon of just 4.3 kilometers in radius. The supermassive black hole Sagittarius A* at our galaxy's center, the largest in the Milky Way, is about 20 million kilometers across. Whenever a clump of matter intersects that black hole, whether a planet, star, cloud of gas, or anything else, only a fraction of the mass gets devoured. The rest gets torn apart and accelerated, where it emits radiation we can observe. We see this around active black holes at the centers of galaxies all the time. The active ones emit spectacular streams of radiation, all thought to be caused by infalling matter. There are hundreds of these X-ray binaries, indicating the presence of many of our galaxy's black holes. Unfortunately, this configuration doesn't describe most black hole systems and so cannot detect most of the Milky Way's black holes. The second way we can do it is by looking at the gravitational waves emitted by black holes orbited by other masses, stars, white dwarfs, neutron stars, or other black holes. These emitted gravitational waves have a specific frequency and amplitude that depends on the masses and separations of the two objects orbiting one another. Since the advanced LIGO detectors began operating in 2015, many dozens of black hole pairs have been found with this technique. Again, unfortunately, this technique can only reveal black holes that are in the actual act of merging with other black holes with present technology. The third way to detect black holes is very new, and it's actually the method used to detect the new record holder for the closest known black hole to Earth, Gaia BH1. By observing an individual star very precisely over time, we were able to detect an unusual pattern to its motion as it moved through the sky. It traced out a helix-like shape as though it was orbiting some invisible, unseen mass. Based on the properties of the star and its observed orbit, we were able to reconstruct that there was a non-luminous object of about 5 times the mass of the Sun exerting a gravitational influence on it. There's a known class of object that fits exactly such a description, a black hole. But again, it's very hard to make sensitive enough observations, particularly at large distances, to detect these tiny perturbations to a star's motion. Meanwhile, the fourth method for detecting black holes, even though it's been the least successful method so far, is the only one that has a hope of revealing most of the black holes we have yet to find: gravitational microlensing. Consider this: not all stars or black holes are in binary systems, and only a fraction of the ones that are have black holes orbiting close enough to emit any signal detectable with current technology. But every black hole, and in fact every mass in the universe, exerts a gravitational influence on the fabric of space itself, causing space to curve wherever it happens to be. As the planets, stars, and black holes in our Milky Way move relative to one another over time, there will eventually be an alignment between any telescope or observatory in our solar system, any black hole that's out there, and a background source of light like a more distant star or galaxy. When this occurs, the background light source will appear to brighten and distort due to the effects of curved spacetime, a phenomenon known as gravitational lensing, or for these little point masses, gravitational microlensing. This enables us to reconstruct the properties of even invisible foreground masses, like black holes. Assuming that black holes are randomly distributed throughout the galaxy, and that there really are a few 100 million of them present, this likely means that the closest black hole to Earth is only around 40 to 80 light-years away. That's a very, very different consideration from the closest black hole being over 1,000 light-years away. All of a sudden, you might not feel so safe, and indeed, we aren't necessarily safe. If a black hole contacts the Earth, of course, it will swallow us. But we don't need to be swallowed in order to suffer catastrophic consequences. If a black hole simply passes very close by the Earth, it would cause what's known as a tidal disruption event, an event where the black hole's gravitational influence on the closer side of Earth is so much stronger than on the farther side that it actually begins ripping our planet apart. Similarly, the top side of Earth would be pulled down relative to the center, while the bottom side gets pulled upward. In short order, the gravitational and atomic bonds holding Earth together can be shattered, transforming our planet from a solid sphere into a thin, stretched debris stream that looks like a piece of spaghetti. In fact, astronomers have named this exact process spaghettification because of the stretching effects that black holes have. As gruesome as that fate is, it would still require a black hole to pass very close to Earth, so close that it's highly unlikely to ever occur. What's more likely, however, is that one of these rogue black holes will pass somewhere within the vicinity of our solar system, where it behaves just like any other mass, tugging on the Sun and all of the planets in a fashion that gets stronger the closer the black hole gets. If a typical black hole passed within the orbit of Saturn or Jupiter, it could perturb the orbit of the Earth around the Sun in such a significant fashion that we'd either get hurled into the Sun or ejected from the solar system completely. That would certainly be a catastrophe for humans. Fortunately, we don't have to be frightened by these possibilities. Instead, we can quantify, based on our understanding of physics and how abundant black holes are expected to be within our universe, the probability of such an event affecting our planet. These three possibilities, a black hole swallowing Earth, a black hole spaghettifying Earth, or a black hole ruining our stable, life-friendly orbit around the Sun, can all be quantified. In order to actually swallow the Earth, a black hole would have to get very close to our planet, close enough that when you factor in how Earth would accelerate due to gravitational attraction, there would be actual physical contact between the Earth and the black hole. Given how many black holes we expect are out there and how long our solar system has been around, that's only about a 0.000000001% chance, or 1 in 100 billion, that any planet would encounter a black hole over the past 4.5 billion years. If you only want to tidally disrupt the Earth, you can be about 100 times as distant and still do it, because a black hole's gravity and the tidal forces that arise because of its effects are just that intense. That increases the odds by a factor of 10,000, to a 0.00001% chance, or 1 in 10 million, over the solar system's history. That's still small, but it's unsettling. It's more likely than you winning the jackpot on a Powerball lottery ticket. But if all you want to do is disrupt Earth's orbit due to the gravitational influence of the black hole, that's a different story. If a black hole comes within about the distance of Jupiter or Saturn, that would be enough to do it, and there's about a 0.01% chance of that happening over our solar system's history, or about 1 in 10,000. Given that there are 400 billion stars in the Milky Way, this has probably happened to several million planets over our cosmic history in our galaxy alone. It's important to remember that in many ways, our own planet and solar system are like getting a single ticket in the great cosmic lottery. There are plenty of extremely unlikely events that, given enough chances, likely to occur somewhere in the universe. With an estimated few sextillion stars in the observable universe and many billions of years of their existence, even unlikely events will happen sometimes. While we normally think about this optimistically, where planets with the right ingredients and conditions can develop life, complex life, intelligent life, and even technologically advanced life, it also works the other way pessimistically. Planets can get ejected, torn apart, or even swallowed whole by all the other objects out there in the universe, stars, stellar corpses, and even black holes. The one piece of good news about all of this is that the odds of any particular catastrophe happening, even over the timescale of several billion years, is very low for any one system. But with enough chances in the universe, it's practically guaranteed that even the most remarkable of these events have happened somewhere at some point within our visible universe. The quest to discover them all will likely be a never-ending enterprise. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.